Place in the Privacy Enhancing Technologies Challenge, featured by the White House. Her PhD is from CMU. Here's the Rising Star and a co-organizer of the workshop. Thank you very much.
Thanks, Natasha, for the introduction. So I know everyone is probably a little bit tired at this time of the day, so I promise I will keep my talk short. And then there's only one thing that I hope people will remember, which is our optimizer that can achieve performance better than Atom, but only requires memory and compute as SGB. I know lots of people keep claiming that, but hopefully we'll show some convincing evidence of our algorithm. Okay, so like one kind of general motivation for a lot of work that I do is to think about where does machine learning data come from, right? Because lots of applications nowadays, they rely on data. And they can come from users or clients or sensors from different distributions, different scenarios, remote devices, and sometimes not even a single entity or single user. It's networks of millions, potentially millions of users or isolated devices or institutions. So the general theme of my work is to move machine learning out of this sandbox. So you cannot think of machine learning data as something that is nicely packaged into you and you just run some off-the-shelf machine learning algorithms to get the predictions. But rather, we need to make sure that our algorithm can scale to modern systems. This is the the direction I'm going to focus on for this presentation. And we also need to make sure that our algorithms can deliver robust performance on complex data. For instance, we have maybe multiple distributions. That's also mentioned in the previous talk, like in continual learning, like that's very common practice. Like how do we deal with those heterogeneous distributions, and how do we deal with the situation where we only have partial observations or even zero observations of the raw data, but we only have some observations of some functions of the data. And then how do we incorporate human preferences in the learning procedure in this noisy setup in the wild, right? For instance, some people may be more risk averse, some people may be more risk seeking, and how do we make sure that we give proper treatment for diverse populations? But in this presentation, I'm going to focus on the first one, which is to scale to modern systems. And specifically, in the context of this talk, I'm going to talk about some efficient distributed optimization algorithms. And that can be applied both for data center settings. So you can imagine that nowadays, lots of the large models, they're trained in across data centers or across thousands of GPU machines and things like that. And then that can also be applied to edge settings. So I start to talk about some setup, but basically where how do we think about different ways to hide communication in this distributed environments. So one popular way to hide communication is to perform local updates. Right? Suppose here this is the canonical objective that we're trying to optimize. Like here fk just the loss on machine k, but ultimately we just want to solve this simple empirical risk minimization objective fw over the model parameters. So suppose we have a bunch of machines in the data centers. Right? Some of them can be, for example, this guy is a central coordinator and a bunch of worker nodes communicating with some coordinator nodes to jointly learn some statistical models. So in practice, there can be many, many ways of implementing things. But here, we're just focusing on this logic layer, like what is happening mathematically. So we may have some global model WT at the current round that is transmitting maybe to a subset of the machines that have their data, right? And then those machines will do some local updates to optimize using their local data and then send these local updates back to the server. So here we call some optimizer to solve this local optimization algorithm. And then those worker nodes may send some model updates back to the server or to some coordinating node. So here is delta 1, delta 2 are the two updates. And then on the server side, the server will want to aggregate those model updates and update the current global model WT to form a new global model by calling some outer optimizer. So after aggregating, there may be different ways to update WT specified by this outer optimizer. So this is essentially a nested optimization framework where we have both inner and outer optimization algorithms. So we can imagine that we can solve this by running a few iterations of SGD. That's one way, like one instance of the inner optimizer. Or you can imagine that we may call some adaptive optimizers like Atom and AtomW to solve this or this. And on this server side, we can just treat those model updates as pseudo gradients, and there are different optimization algorithms there we can call as well. And this is popular for data center distributed training. So here I'll just write the procedure maybe in a slightly more formal way. So at each round T, then for each node I, so suppose we have n nodes in total. Each node just update xt. Oh, here maybe some abuse of notations. Previously we're talking about WT, but here we're using xt to denote the model parameters. So update the model parameter xt with some inner optimizer and send the model updates back. And then on the outer layer, we first aggregate or just simply average those updates deltas and then call some outer optimizer. So what are the challenges in this setting? Okay. That specifically in this work that I'm going to talk about, one is we are looking at this heavy-tailed stochastic gradient noise. So this is especially true for like attention-based models. So lots of the works, either empirically or theoretically, have identified that heavy-tailed stochastic noise can be very detrimental to, in terms of destabilizing this entire training process, and sometimes they can even cause things to diverge completely. So, for example, these figures are taken from previous papers, from others' papers. And this is a ResNet model, and they show that this gradient, the stochastic gradient noise, is following this nice symmetric distribution, and it's light-tailed. But if we use BERT, which is some attention-based models, and then this stochastic gradient noise may form like heavy-tailed, and this breaks lots of the assumptions and methods that people use in previous optimization algorithms, and we need some better mechanisms to deal with such heavy-tailed gradient noise. So another challenge that we looked at in this work is that the adaptive optimizers, which is usually the default optimizer that people call when they optimize for large models, simply because SGD wouldn't even converge in lots of the settings. So by default, people use things like Atom or AtomW, and but they can be very costly, mostly because to achieve good performance, good convergence by using those adaptive optimizers, we need to pay additional costs in terms of the extra memory and systems, like memory and compute overheads. So here I'm showing two like adaptive optimizers, not Atom, but in the like the costs are similar in the sense that in AdaGrad here, so this gradient f of WT is preconditioned by this GT, which we call the preconditioner. That's just constructed using some gradient statistics to transform the gradients so that we can get better condition numbers, so that we can just adapt to the underlying geometry of the problem better to speed up convergence. And that's also true for MSPOP, where this preconditioner is essentially some estimate of the second moment of the gradients. And effectively, what they're doing is that they're allowing for this per coordinate learning rate. So instead of using uniform learning rates across all the coordinates, those adaptive optimizers, they allow for the usage of per coordinate learning rates. And intuitively, you can imagine that if we have some real features, real signals, and you really want to amplify that real and informative coordinate, you can just use a larger learning rate on that coordinate. Whereas if you have a very common, non-informative, but very large coordinate, you want to ideally you would like to just use a smaller learning rate on that coordinate. And that's intuitively what adaptive optimizers are doing, and that's why they're useful. Although it's still an open question to rigorously understand why they're useful. So our key insight that I'm going to talk about is that these two challenges are inherently related because preconditioning can be viewed as soft clipping. And then we propose one method to address those two challenges at once. And that is the new optimizer that we developed, which we'll call bi-clip. And we're doing corner-wise clipping from both above and below. So now I'm going to illustrate what is bi-clip, what it's doing, and why it's useful. So suppose this is our gradient vector. Some values are big, some values are small, and then some are positive, some are negative. We're doing that after applying bi-clip. We're transforming this gradient vector into something like this by both clipping from above and below. So this is clipping from above. So the gradients with large magnitudes will get rescaled to be a smaller value by some threshold. And clipping from below means that the small gradients that is smaller than the second threshold that we use for the clipping from below will get magnified. Like we will just rescale the small coordinates to some larger value up until the second threshold that we set. So I talk about later that because we're doing sort of some way of clipping, and we can easily get convergence, and it's also easy to reason about convergence under heavy-tailed noise because we're doing this specific form of clipping, then that gives us an effective way to handle this heavy-tailed distributed noise. And another benefit is that here we're not doing uniform clipping, and you can imagine that this can be sort of think of as the procedure as we are just reducing the signals from the big gradients, but we are amplifying the signals from the small but rare coordinates. And then that just gives us benefits of adaptivity without maintaining the preconditioners. So the only, the additional cost is basically two scalars. One clipping from above threshold, and one number which is the clipping from below threshold. And that's the two additional hyperparameters. And we will show that it's useful in centralized training as well. So in the context of this work, we mostly apply this optimizer to distributed environments. But as a side product, it's also very effective and useful in centralized training. So here is just a more detailed illustration of the behavior of bi-clip. And this is the formal definition. X is the gradient vector, and xj is the jth coordinate of that vector. So that's the number. And here, UD are just two numbers and two thresholds. So D is the upper clipping threshold, and U is the lower clipping threshold. And here, this C is just the indicator function. So this equation may be a little bit complicated, but essentially what it does is that when we have some coordinate xj with some absolute value that is greater than U, we just rescale this coordinate so that this xj is equal to U. On the other hand, if we have some xj that is smaller than D, we increase that xj so that it becomes D. So here I'm showing the benefits of bi-clip in centralized learning. So recall that what we are doing is that we're just doing this rescaling of different coordinates of the gradients in a principled way. And we are not using any additional gradient statistics, or not tracking any information, not storing any additional thing. So this is VIT on, fine-tuning VIT on CFAR 100, not a very large scale data set or model architecture. We see that, so SGD is not too bad, but just converges much more slowly than Atom and bi-clip. So Atom and bi-clip, they are almost the same here on this data set. But remember that Atom almost needs 3 times the memory. Like it needs some estimates of the first moment and the second moment of the gradients. Oh yeah, this is on the text data. So everything here are now in the centralized learning where we're just using a bi-clip optimizer. We see that this is fine-tuning this recent language model Q1 2.5 on the score dataset. We see that here SD is much worse than both Adam and bi-clip. But we also tested on other datasets that bi-clip can sometimes outperform Adam after very extensive hyperparameter search. In our papers, in the appendix, we have maybe 6 or 7 pages only describing hyperparameter search and what are the optimal hyperparameters we use. Yes.
And do you consider the same threshold for all the elements of the gradient? Do you consider the same threshold, both of the thresholds that you consider, the upper threshold and the lower threshold? They are the same for all elements of the gradient vector?
Well, that's a great question. And that's the current limitation of this optimizer. And that's one direction we're currently working on is that we have to tune this threshold for different data sets. So like they are not robust to different model architectures yet. That's a great point. Okay, now going to the distributed setting, we would like to apply this bi-clip optimizer at both inner and outer layers. So what we're doing is that we can update this XT using gradient-based methods with this bi-clip gradient optimizer and get the model updates and send the updates to some coordinating node so this coordinating node will get some pseudo gradients, which is the updates from all the worker nodes. And again, this coordinating node can apply bi-clip on top of these pseudo gradients to update the model parameters for the next round. So what we're doing is that we're doing this approximate preconditioning both locally and globally. And it outperforms applying bi-clip only on the local side, and it also outperforms applying bi-clip only on the global side.
There is a new workshop.
Yeah, so we call this because we're applying double bi-clip. We call this entire algorithm in this distributed training setting bi-squared clip. So more broadly, what we come up with is this general framework, which we call TEL-opt, along with a series of instantiations and convergence analysis to handle heavy-tailed stochastic gradient noise with different inner and with basically general choices of inner optimizers and outer optimizers. So for instance, these inner optimizers, we can use bi-clip, we can use L2 clipping, which I think is proposed by some previous works. Here L2 clipping is just you clip the gradients to some max L2 norm. Like basically if some gradient is too large, you just uniformly rescales each coordinate of the gradient so that the entire L2 norm is smaller than some threshold. We can use Adam, we can use SGD, we can use acceleration algorithms. And that's the same for the outer optimizers. This is one instance. So if we use inner as SGD, here we just run k iterations of stochastic gradient descent on XTI to update. And outer, we're just using this simple average. Then we just call this entire algorithm, I think, average dash SGD. Yeah, this is just some naming. And another instance is that if we're using this simple average as the outer optimizer and bi-clip as the inner optimizer, we're calling it average bi-clip. Okay, and then we also have some analysis of TEL-opt, which hasn't appeared in previous works, especially under heavy-tailed gradient noise and clipping. And clipping is a little bit tricky to deal with because once you consider clipping, then the gradient estimates will no longer be unbiased. And so you will need some additional assumptions like to get some convergence guarantees. What we're doing here is that we're scheduling this clipping threshold as training proceeds. So we are increasing the upper clipping threshold and we're decreasing the lower clipping threshold. So that the hope is that at the final stage of the training, the clipping does not happen. So that's what we used in the analysis as part of the assumptions or the conditions for the convergence to hold. And another thing that is notable here is we are assuming the heavy-tailed gradient distribution. What does that mean is that the alpha's moment of the stochastic gradient, or the expectation of the alpha's moment, is bounded by b to the power of alpha for alpha equal to, for alpha in 1 and 2, not including 2. Because when alpha 2, then that's just the standard bounded variance assumption. But as we talked about before, that the gradient distribution can be very heavy-tailed, and the variance of the stochastic gradients may be unbounded, and that's something that cannot be handled very well in previous literature. But here we are only requiring this alpha moment to be bounded, but we are allowing the variance of the gradients to be unbounded. So I will not talk about the technical details of the proof, but at a high level, we get that for potentially non-convex functions, we can obtain suboptimality epsilon in terms of the gradient norms after t rounds, where t is basically 1 over epsilon squared. So that means that our convergence rate is around 1 over square root of t for non-convex functions, non-convex and smooth functions. And we know that this rate matches the previous results, which have stronger assumptions with bounded gradient variance. So that means our result is stronger because we get the same convergence rates with a weaker assumption. But one current limitation of our analysis is that, so there are potentially many different instantiations of this tail-off framework. We are only able to prove this good rate of convergence for most of the instantiations, but for some instantiations, our rate is worse, and that's still an open question. Any questions so far? Next, I'll be talking about some of the empirical aspects of using both synthetic data and real data. And the way we look at synthetic data is because we want to control the noise manually so that we can explicitly show the effects of the noise distributions to the convergence. So for instance, here, this Gaussian distribution is not heavy-tailed. It was light-tailed. X-axis is the number of alternate steps. Y-axis is basically measuring how close our learned model parameter is to the optimal model parameter. On this synthetic data set, we are just manually adding some Gaussian noise, and that's not heavy-tailed. We see that essentially all those different methods, they perform very similarly, can achieve a good convergence at the end. But maybe with slightly different speed. But here on this right figure, we are looking at the convergence on this synthetic data with T distributions. That is a heavy-tailed distribution. And we see that for the average SGD-based method, which is the topmost line, it just never converges. Whereas using our method, biclip as the inner optimizer, so atom biclip, that converges the best. And atom squared is just using atom on both outer and inner layers. We see that is not as good as atom biclip.
So what is the difference between the atom biclip with the average biclip? And what's the difference?
Average
Third
biclip.
one, yeah. Right.
So they're all using biclip at the inner optimizer, and it just average is using the simple average at the outer optimizer, whereas atom, it uses atom at the outer optimizer.
Okay, but where is that the middle curve, the average biclip, which curve it is?
That's the green line, I think. Oh, there's some color. Let me see.
That overlap
That's
with
this
the other
one.
curve?
That's this one. This line.
Oh, okay.
Yeah. It's still worse than using atom as biclip.
Okay.
Yeah, but if we compare these two lines, then that shows the effects of biclip on the inner optimizer.
Right.
Yeah.
Okay, thank you.
Okay, so this kind of validates our hypothesis on the synthetic data. And on real-world data, we look at different types of model architectures. And lots of previous works have already shown empirically that the stochastic gradient noise is heavy-tailed. So they can just simply plot out the gradient distribution and see that's heavy-tailed. And we also did that in our paper, but I think that's the consensus. So for these transformer encoders, we're looking at not a very large-scale model on like fine-tuning BERT model on this glue benchmark. So it's basically a bunch of language tasks, and then people care about like the average performance across all the tasks. So these are all the sub data sets in that glue benchmark. And here are different metrics, accuracies or F1 numbers or these correlation numbers. So basically the higher the better for all the metrics. And finally we report the average in the last column. Here we're showing that in this sub table, we show that if we fix the outer optimizer to be simple average, and we choose the inner optimizer as atom or biclip, we can get we can get good performance by using atom. And then like this biclip is sort of close, but not as good as using atom. But this is only the case for the outer optimizer being average. So this means that using atom or biclip as the inner optimizer, it's really improves the performance significantly, especially compared with using SGD or just L2 clipping. By the way, average SGD and average L2 clip, there are some instances of our framework they have appeared in previous works but not analyzed under our assumptions. Okay, and then this is the second half of the table on the same task, same data set. We show that also we compare with atom biclip, atom squared, dilocal, which is a recent method. I think it's using some adaptivity on the inner optimizer side and using acceleration on the server side at the outer optimizer. It's also widely used. And bi-square clip is our proposed method. We can see that on this glue benchmark, in terms of the average performance, almost 1.5 absolute value, like 1.5% better than the best method, which is dilocal. It's proposed in previous works. And another thing that we should note is that all the other methods that we compare against in this table, they are much more inefficient than bi-square clip because they need to maintain additional gradient statistics either on the outer optimizer or inner optimizer. And that is in the same dimensionality of the gradients. So for instance, atom squared needs to use atom on both sides, and dilocal needs to use adaptivity on the at the inner side as well. Oh, and another side note is that about this dilocal recently, there's this empirical paper from Google that basically what they're doing is that they're spending 32 pages running experiments like showing that dilocal is good. What they call like scaling laws for dilocal, and then they show in this paper that dilocal is harder, better, faster, and stronger. But it's very interesting that at least in the settings that we tested under very, very extensive hyperparameter search, bi-squared clip is better than dilocal on every data set, while being more efficient. Okay, so this is another model that we tested, generating model on the machine translation task. The data sets are like TED Talks and news commentary. And we see again that bi-squared clip can outperform atom squared and also some other optimizers.
What do you mean the generative model? Which model are you testing here?
I think we are fine-tuning the T4 model.
T4?
Yeah. Oh, and another note is that we also apply tail opt so which is our framework to federated learning. And that's a special case of distributed learning where we have more constrained systems requirements. And hardware may be different, network connectivities can be very slow. Different devices may have different battery powers and have different non-IND distributed data. Like different users may have different styles of using their devices. The communication can be very expensive. So it's not in the data center environment. So we also tested on the federated learning data set. We look at the perplexity score on the Shakespeare data set. We see that average plus biclip is much better than. So here the perplexity score is lower the better. So it's better than L2 clip and also than SGD. So summary. There are still lots of open questions in training large models efficiently, and some of the challenges we looked at in this work is the heavy tail stochastic gradient noise and the expensive adaptive optimizers. So we proposed biclip, which is a principled approach to addressing both of these challenges, achieving atom-like performance with SGD-like memory and compute. And we give general convergence bounds considering clipping, considering heavy tail noise, considering all those practical, challenging assumptions. So we can use biclip in centralized training as a new optimizer, but we can also use biclip at both inner and outer optimizers in distributed environments to further boost up the performance in distributed optimization. I'm very excited about this direction, and there are lots of interesting future works. One is, of course, to run larger scale experiments, ideally in pre-training settings. We're also collaborating with other people on this, because currently our experiments, though very rigorous, only focuses on fine-tuning settings. So we hope to do something in this pre-training setting. And the second is to understand heavy tail noise in asynchronous training, because I think in practice, as Morsham talked about, there can be different stragglers, and then I think maybe in this entire complicated training pipeline, there's some sort of asynchrony that people use actually in training large models in practice. For example, if in that pipelining system, and if there are too many bubbles, maybe we're willing to sacrifice a little bit of asynchrony just to get better runtime performance trade-off. And I think heavy tail noise is something inherent for attention-based models. It's just interesting to understand heavy tail noise in asynchronous settings. And another interesting direction is to explore the natural connections between clipping and mixed precision, because you can sort of thinking of mixed precision training as a way of doing some soft clipping as well in the training process. When you reduce things to lower precisions, you're essentially clipping them to different thresholds. Yeah, I think general, the goal is to just close the gap between what people do in practice and what we can understand in theory, and explore that both theoretically and empirically. And of course, another open question is to understand why do we need adaptive methods. I think that's something that has lots of extensive research has been studied in this front, but that's still an open question and very interesting. And our paper is available online. If you're interested, you can check it out, and we will also release our code very soon after we finish the camera-ready paper. And thanks, I'm happy to take questions.
I have one question. Based on the heavy tail nature of the stochastic gradient that you consider in this work, does this happen uniformly over all the entries of the gradient, or does it's happening partially over some kind of elements? Because if it's partially, then the idea of by clipping just for the lower part, the lower threshold doesn't have any sense.
What do you mean?
For example, when when you consider this heavy tail noise, so this is like a part of that is actually inherently in the gradient, right? So is this does this happen partial, some elements have this property and the other, doesn't experience such kind of noise? Do you understand?
Well, I think it's just the entire gradient, the entire stochastic gradient, their noise is heavy tailed. So the noise is the full gradient minus the stochastic, the noise is the full gradient on all the training data minus the stochastic gradient, and that variable is having heavy-tailed distribution. Yeah, that's good. Other questions?
For large-scale experiment, have you considered like cross-node and or even cross clusters and multi-data center training? Would that affect, because there's a communication and all reduce all those sort of strategy? If you like effect, like how you like gradient, how will back propagate the gradient, then the effect the strategy you currently use?
That's a good point. I think so. We considered some of that. For instance, here we're using like low cost is only those nodes. So suppose these are in different servers, or maybe they're in different data centers in the extreme case. For those nodes, they only accumulate updates locally before they send anything back to some coordinator. And I think in our current experiments, we didn't really do like real distributed training, like implementing those sending, receiving messages, API those, because we focus on the statistical properties. Like we're just running simulations of these distributed environments. But I think the goal is to come up with something that is fully scalable in that setting. And I think in addition to local updates, people have also used some other methods, mechanisms to like speed up communication. I think that's also orthogonal too. Yeah.
Thanks.
Thanks. Yep. Okay, thanks everyone. Okay.
Please join us for the poster session. It's kind of around the corner. Okay. If you can, and if not, thank you very much.